Good day, everyone. I am Samantha Rose de la Punta, and together with my partner, Giovanna Gia Gonzalez, it is our pleasure to welcome you to our presentation entitled Optimization of Print Parameters of 3D Printed PLA PVA Separators for Microbial Fuel Cells. Microbial fuel cells generate electricity directly from substrate energy with high efficiency, eliminating the need for additional gas treatments like carbon dioxide removal. The performance of MFCs heavily depends on the surface area of the proton exchange membrane and cathode, which are essential for optimizing energy transfer and system efficiency. The research objectives includes the evaluation of the performance of the 3D printed PLA PVA separator in microbial fuel cell, the comparison of the tubular and flat plate design of the microbial fuel cell separator through proton conductivity testing, and the integration of the optimized 3D printed separators into microbial fuel cell, and evaluation of the performance based on power density.
The significance of this study extends beyond technological innovation, aligning with global sustainability goals. It contributes to Sustainable Development Goal SDG 6, specifically Target 6.3 by promoting water use efficiency across sectors and supporting sustainable freshwater management to address scarcity and reduce the number of people affected by it. Additionally, the study supports SDG 7, particularly Target 7.2, by advancing the integration of renewable energy into the global energy mix, aiming to increase its share by 2030. Scopes and limitations. The study assessed the performance of 3D printed PVA PLA separators in MFCs, focusing on power density. It examined the impact of thickness, resolution, filament composition, and configuration while maintaining consistent print speed and temperature. Performance was evaluated through proton conductivity and power density, highlighting the influence of printing parameters on MFC efficiency. The study evaluated MFC separators excluding electrodes, anodes, effects of porosity, surface area, biofilm effects, and bacterial population. It focused solely on PLA and PVA filaments without testing other materials or conducting long-term durability and COD removal assessments.
This schematic diagram outlines the steps of our study. We began by preparing the necessary materials for constructing and assembling the microbial fuel cells. Next, we 3D printed mixed PVA-PLA cylindrical and flat plate separators for proton conductivity testing to identify the configuration with the best performance. We then optimized the printing parameters for both mixed PVA-PLA and pure PLA cylindrical separators in the microbial fuel cell setup. Voltage was measured over 10 days in two ways: open circuit and closed circuit voltage measurement. Also, current was calculated using Ohm's law. Polarization testing followed, and finally, statistical treatment and interpretation of the results were conducted to analyze the findings.
For power density data acquisition, a digital multimeter was used to measure voltage and resistance. The current was calculated using equation 1, and the power output was determined from the measured voltage and calculated current using equation 2. Power density was then computed using equation 3. For data analysis, to assess proton conductivity differences, data, proton concentration versus time was fitted to a cubic curve in MATLAB. The second derivative of the equation was calculated, and the x value corresponding to the maximum proton conductivity was determined. These maximum values were analyzed using a one-way ANOVA to identify significant differences between the samples. To evaluate whether the two varied print settings of each parameter showed significant differences, the power output of the samples was analyzed using a three-way ANOVA. Additionally, current, voltage, and power data were individually subjected to a one-way ANOVA to assess their variations.
The performance of the flat plate separator and cylindrical separator for proton and conductivity testing. Figure 1 shows the concentration trend over time for cylindrical separator demonstrating that the separator effectively facilitates proton movement from the cathode to the anode, as indicated by the decreasing pH in the anode chamber. This suggests good proton conductivity and efficient ion transport. Additionally, the absence of HCl leakage into the anode region highlights the separator's selectivity. In contrast, Figure 2 shows minimal change in proton concentration with a flat plate separator, indicating potential limitations in conductivity. The slope for the cylindrical separator, which is 9.52 times 10 raised to negative 5, suggests efficient proton transport, while the flat plate separator's slope, negative 9.79 times 10 raised to negative 8, indicates negligible or detrimental proton transfer, confirming the superior conductivity of the cylindrical separator. After doing statistical analysis, it was indicated that there is no significant difference between the two configurations. It has been observed in previous studies such as Ramirez-Nava in 2021 that as membrane thickness increases, membrane resistance increases, leading to a decrease in proton conductivity. In this study, the consistent material and controlled hydration conditions in both separators likely contributed to their equivalent transport efficiency. This suggests that under the given testing parameters, the geometry or configuration of the separators does not significantly affect proton conductivity.
Based on the three-way ANOVA, there was no significant difference in power output among the varying print settings. The minimal variation between their settings were unlikely to have a substantial impact on the separator's performance. Figure 1 compares the current, voltage, and power outputs of the 8 samples based on their thickness. Samples with a 3 mm thickness consistently outperformed those with 2 mm, highlighting the significant impact of separator thickness on MFC performance. Thicker membranes reduce reactant crossover, preserving redox reactions and enhancing overall efficiency. Statistical analysis showed that the difference in resolution 0.1 mm versus 0.2 mm had a minimal effect on ionic transport and separator performance in microbial fuel cells. However, surface roughness influenced by resolution apparently impacted MFC efficiency. Separators printed at 0.2 resolution had higher surface roughness, which promoted biofilm formation and reduced oxygen crossover, improving the anaerobic environment in the anode. As a result, separators with 0.2 mm resolution perform better than those with 0.1 mm resolution as seen in Figure 4. Statistical analysis showed no significant difference in power output between pure PLA and mixed filaments. However, pure PLA separators consistently outperformed the mixed filaments as seen in Figure 5. The water solubility of PVA increased the porosity of the separator after soaking, allowing greater oxygen diffusion, which disrupted the anaerobic environment necessary for electrogenic microbes. This resulted in reduced electron availability and hindered microbial activity. Maintaining low oxygen diffusion was essential for preserving anaerobic conditions and optimizing our microbial function to maximize electrochemical performance. Statistical analysis at alpha equals 0.05 revealed significant differences in current, voltage, and power outputs among the 8 samples. The two key tests identified 7 pairings with significant performance differences, all involving run I, except for run E. Run I outperformed the other configuration, showing superior outputs due to its optimal combination of pure PLA, 3 mm thickness, and 0.2 mm resolution. Comparisons among the remaining samples showed no significant differences, highlighting that variation in material and print settings alone were insufficient to achieve similar performance.
Figure 4 shows the sample polarization curve for run F with 2 mm thickness, 0.1 resolution, and with pure PLA composition. According to the results, the superior performance of the separator in run D with 3 mm thickness, 0.1 resolution, and a composition of 30% PVA and 70% PLA is attributed to the inclusion of polyvinyl alcohol, whose hydrophilic nature enhances ionic conductivity, a key factor for efficient ion transport in microbial fuel cells. This separator achieved the highest maximum power output due to its ability to reduce resistance and optimize electrochemical process. Additionally, the results highlight a relationship between resolution and separator thickness, where at zero point 0.1 resolution, a thicker separator enhances stability and performance, while at zero point 0.2 resolution, a thinner separator maximizes material efficiency and minimizes resistance, showcasing how variations in these parameters influence power output.
Nafian's excellent ion exchange properties resulted in higher power densities in MFCs compared to 3D printed separators. Run-I achieved the highest power density among the 3D printed separators, but it was still much lower than Nafion 117 and other variations of Nafion. Other 3D printed configurations performed even worse, showing that Nafion membrane outperformed the 3D printed separators overall. Nafion has a high environmental impact due to its petroleum-based production and non-biodegradability. In contrast, PLA is biodegradable, made from renewable sources, and has a lower carbon footprint. PVA is more eco-friendly than Nafion as it can biodegrade under certain conditions. PLA and PVA are also more cost-effective than Nafion, making them better options for budget-conscious applications. In conclusion, the study demonstrated the potential of 3D printed PLA and PVA PLA separators for microbial fuel cells, with RAN-I achieving the highest power density among 3D printed separators, though still lower than Nafion. While flat plate and cylindrical separators did not have significant difference in proton conductivity, cylindrical designs offered better mass transfer efficiency. Optimal performance was linked to 3 mm thickness, 0.2 mm resolution, and pure PLA material. Polarization studies revealed that finer resolutions benefit from thicker separators for stability, while coarser resolution enable thinner separators to enhance material efficiency. Despite their promise as sustainable alternative, further refinement was needed to optimize mechanical stability, ionic conductivity, and oxygen diffusion of PLA filaments.
We have come up with three recommendations after conducting the experiment. Number one is that future studies should incorporate chemical oxygen demand removal testing to evaluate the separator's ability to reduce organic pollutants, which is a critical parameter in wastewater treatment application. Number two is that conducting scanning electron microscopy is highly recommended to examine the physical properties of the separators. SEM can reveal detailed information about surface morphology, pore structures, and material uniformity, which are essential for understanding the separator's behavior in microbial fuel cell systems. Lastly, for studies that involve fabricating filaments from pellets, it is crucial to partner with a reputable filament manufacturing center to ensure the production of high-quality filaments. Consistent thickness is particularly important as 3D printers are highly sensitive to filament irregularities, which can lead to printing failures or compromise structural integrity of the printed separators.
That concludes our presentation. Thank you for your attention and we hope you have a wonderful day.